Welcome. Get ready to learn all about math as you've probably never seen it before. You'll learn how to do addition, subtraction, multiplication, division, fractions, squaring, and even algebra. What's so different about that? Well, you'll learn how to do it in your head with Mathemagics. Now, get ready to learn all about Mathemagics with Professor Arthur Benjamin.
Welcome to Mathemagics. If you think about it, numbers are everywhere. And the more sense you can make of numbers, the more successful you will be. I promise that if you watch the video, listen to the audio tapes, and practice with the workbooks, you will improve your ability with numbers. Now, the most commonly used mathematical operation is addition. Whether you're counting calories or figuring out the bill at a restaurant, I have some valuable tips for you. Welcome to Mathemagics. We'll start by talking about addition, which is the simplest operation. Remember from the Foothill Country Day School when Corey added that long series of numbers?
Now this is Corey, and I hear you're pretty good at adding numbers in your head, is that right?
Yeah.
Can she really add a lot of numbers in her head? Yeah. Okay, I'm going to give you some complex problems. You add up all these numbers in your head, and I'm going to use my trusty calculator here that I just bought. You ready for this?
Yeah.
Okay, here we go. What is 532 plus 463 plus 837? How much is that?
1,832.
She's right. Look at that. That's pretty good.
That was easy.
That was easy?
Well, by the end of this video, you will also understand how to add numbers in your head just like that, and with practice, you'll be able to do it just as quickly. I like to explain everything by example. Let's start with two-digit numbers plus two-digit numbers. Okay, so the first problem we'll do will be 54 plus 41. Now, the most important thing to learn about mental calculations is that almost all of your calculating will proceed from left to right. Now, that's the opposite of the way that we're taught in school, where we learn how to do things from right to left. Right to left is fine for doing the math on paper, but if you do the math in your head, you'll see that it's much faster and much more natural to do the problem from left to right. After all, we read from left to right, we pronounce numbers from left to right, we say 54, not 4 and 50, and I claim that with practice it's a lot easier to calculate from left to right. Okay, so let's do 54 plus 41 here. We start with 54 plus 40, and then we'll add 1. Now 54 plus 40 is 94. 94 plus 1 is 95, and that's the answer. Now if that 54 plus 40 was giving you any kind of trouble at all, then I recommend that you start with the audio tapes and listen as we warm up doing what I call one-digit problems, okay? Let's go on to the next problem, 46 plus 33. Okay, well, 46 plus 30 is 76. 76 plus 3 is 79, and that's the answer. Here, let's try a problem that's a little more difficult that involves carrying, but it's not too difficult. Let's try 87 plus 52. Now, what's 87 plus 50? Well, 8 plus 5 is 13, so 87 plus 50 is 137, right. Now you add 2 to get 139, and that's the answer. Now, if I'm going too fast, you've got the remote control here. Use that pause button, use that rewind. I've just got so much material that I want to cover, I may be going a little quickly for you the first time. Also, before we get on to any harder problems, you should be exercising using our workbook. Okay, do as many problems as it takes for you to get up to speed. Let's do another problem with carries, though. Let's say 58 plus 25. All right, 58 plus 20 is 78. 78 plus 5 is 83, and you're done. Here, you try this one. Try doing 49 plus 32. Okay, so what do we do first? 49 plus 30, that's 79. 79 plus 2 is 81, and we're done. Let me give you another way to do this problem. One of the great joys of doing math in your head is that there's often more than one way of solving the same problem. Look at the number 49. You know, that's 1 away from 50. That's 50 minus 1. So let's do 49 plus 32 by adding 50 plus 32 to get 82, and then subtract 1 to give us 81. Wasn't that easy? Here, you try that same strategy with this problem, 86 plus 79. Okay? 86 plus 80 is 166, and now you subtract 1 to get 165. Okay, now at this point, I insist that you stop right here, go to the workbook, practice the 2-digit plus 2-digit problems, because only once you're good at doing that will you be able to go on to the next level when we start addressing 3-digit numbers, okay? All right, are you back? Are you ready for more? I hope you've done the problems in the workbook, but if you haven't, well, proceed at your own risk. At least you'll be able to understand what we're doing. It may take a bit of practice before you're up to speed and actually able to calculate the way we're doing it. Okay, let's do 345 plus 23. That's a 3-digit number plus a 2-digit number. Okay, we start by doing 345 plus 20. That's just a 1-digit problem, which you should be good at if you've listened to the audio tapes. 345 plus 20 is 365. Now you add 3 to get 368. Okay, let's up the ante a bit. Let's do 345 plus 523, adding 2 3-digit numbers now. Okay, we're doing everything from left to right. So first we're going to add 500, then 20, then 3. Okay, ready? 345 plus 500 is 845, right. Now we add 20, 845. Wait, let me stop here. What has the problem become? The problem's become 845 plus 23, right? Okay, pause there and now go on. 845 plus 20 is 865. Plus 3 is 868. And that's the answer. Here, let's try one that's a little more complicated and a little more practical too, because we're going to be using money. All right, let's say I want to add $8.46 to $7.25. Okay, just as usual, we're going to work from left to right. Start by adding the $7 to the $8.46, and we have $15.46, right? And now we have $15.46 plus 25 cents. I add the 20, gives me $15.66, plus 5 is $15.71. Okay? Let's do one more problem. This is a special kind of problem, but it's one that shows up a lot when you're using money. I'm going to add $6.37 plus $2.99. Okay, now $2.99, you see that a lot. Oftentimes when you buy items, you're 1 cent away from an even dollar amount, or maybe 5 cents away from an even dollar amount. And I'm going to take advantage of that. Let's do $6.37 plus $3 first, because that's so easy. It's $9.37. But we added 1 penny too much, so we subtract the penny, and now we're left with $9.36. Okay? Let's now go back to the Foothill Country Day School and see Corey adding up her numbers. Now, she added up more than 2 numbers, but that's okay. We're adding the digits 1 number at a time, so it always seems like we're only adding 2 numbers at the same time. Let me explain. Go ahead, Corey. Let's see what she's doing here.
What is 532 plus 463?
First, she had 532 plus 463. Now, freeze right there. At this point in the calculation, Corey should have been adding the 400 as Mike was saying the number. So went 532 plus 400 and, while he was saying and, she should be adding that 400 right now so that she's instantly thinking of 932 plus the rest of the number, which was 63. Okay, so she's heard 532 plus 463. She's now thinking 932 plus 63, which is 995. Right. Now, stop. Look at the number, 995. That's a special number. That's just 5 cents or 5 numbers away from 1,000. 995, so she should be thinking 995, that's 1,000 minus 5. I'm going to add 1,000 minus 5 to the next number. The next number was what?
837.
837, so 1,000 minus 5 added to 837, that's 1,837 minus the 5 is?
1,832.
Which was the answer? Good for you, Corey. Okay, I'd like to end this module by giving one other practical application of addition, and that's for calculating tips. Let's say you were having dinner and the bill came to $42, and you wanted to decide to leave a tip of some sort. Now, if you were a cheapskate, you might leave a 10% tip, which at least is easy to calculate. 10% of $42, that's easy. You just move the decimal point over 1 and you have $4.20. But that's not much of a tip. You might decide to be generous and leave a 20% tip, and that's good. That's easy to calculate. All you have to do is double the $4.20 that we calculated, and that gives you $8.40. Suppose you want to leave an amount that's in between, let's say 15%. 15% is also very easy to calculate. Take the cheapskate amount of $4.20, add half of that. What's half of $4.20? Well, it's $2.10. We'll talk more about doing division in a later module. $4.20 plus $2.10, add them up from left to right, and you get $6.30, which would be exactly a 15% tip. And I hope these tips will be very useful for you. Have you ever tried to stretch your budget a little bit too far? Well, hopefully if you learn mental subtraction, you'll never write a rubber check. Now it's time to learn subtraction. Do you remember from the Foothill Country Day School when Chris did that subtraction problem in his head? Let's take a look at that.
All right, Chris, ready for a little mental subtraction here?
Okay.
What is 1,231 minus 589? How much is that?
642.
Yep, in his head. Look at that. Can you believe that?
By the end of the module, you will also know how to do problems just like that with just a little bit of practice. Okay, let's start off very small with subtracting 2-digit numbers, and we'll work our way up. Let's say we wanted to do the problem 79 minus 43. Well, just like with addition, we do all of our calculating from left to right. So first we're going to subtract 40, then we're going to subtract 3. Now 79 minus 40 is 39. 39 minus 3 is 36, and that's the answer. Now, if any part of that problem gave you trouble, you should go back to the audio tapes where we warm up subtraction with 1-digit problems. Okay, let's go up a level and try this one. 87 minus 35. All right, now 87 minus 30 is what? 57, good. Minus 5 is 52. And that's it. 52 is the answer. Let's do another problem. 83 minus 49. This will be a little bit more difficult. First we do 83 minus 40. Well, 83 minus 40 is 43. Minus 9 is what? 34. Now, I'll bet you had a little bit of trouble with that last subtraction. 43 minus 9 is 34. You might remember that 13 minus 9 is 4. But let me suggest an even easier way of doing this problem. In fact, we'll be doing a lot of our subtraction problems this way. Let's, instead of subtracting 40 at our first step, let's subtract 50 instead. So 83 minus 50 is what? 33. But you've subtracted 1 too much, so you have to add the 1 back, and you're left with 33 plus 1 is 34. Wasn't that simpler? Let's try another problem. You try this one, 91 minus 37. So start by subtracting 40. 91 minus 40 is 51, right? And now we add 3 back to that. 51 plus 3 is 54. Wasn't that easy? Let's try another one. How about 71 minus 25? We'll start by subtracting 30, then we'll add back 5. 71 minus 30 is 41. 41 plus 5 is 46, and you're done. Now you should do some exercises in the workbook before we do the 3-digit subtraction problems. Make sure you're good at those before you go on to the next step. Okay, welcome back. At least I hope I'm welcoming you back. If you've just been watching this, that means you haven't been doing your exercises, and the only way to build those mental muscles is to work those exercises. Okay, let's try 357 minus 23. Okay, well, we'll start off with 357 minus 20. Okay, 357 minus 20 is 337. That should be easy. Okay, 337 minus 3 is 334. Okay? All right, that was our transition problem. That took us from 3-digit numbers minus 2-digit numbers. Now let's do a 3-digit number minus another 3-digit number. Let's do a similar problem, 457 minus 123. Okay, well, the first thing, again, we do all of our calculating from left to right, so we'll subtract off 100. 457 minus 123, well, after I subtract 100, my problem becomes 357 minus 23. Hey, and that was the problem we just did. And we got the answer of 334 that way. Okay, let's try another problem that'll seem hard at first, but once you see the sneaky way of doing it, it'll be very easy. Let's try 743 minus 295. Now, if you subtract 200 and make the problem 543 minus 95, this point it might get a little bit scary. So I have another suggestion. Let's start the problem all over again. 743 minus 295. Let's subtract too much. Let's subtract 300. Okay, 743 minus 300 is what? It's 443. But we've subtracted too much. How much too much? 5 too much. So we have to add the 5 back to get 448. You see the strategy? This is a useful thing to know because lots of things, prices are often end in 95, 99, and so on. Let's try, you try this one. 826 minus 399. All right, so what are you going to subtract? Not 300, but subtract 400. That's right. 826 minus 400 is 426. Add back the 1, and you've got 427. Let me remind you again, if I'm going too fast for you, that's what the pause button is for. That's what the rewind button is for. You need to go over this several times. Be my guest. Spend as much time as you need. Now, before we begin doing even more complicated subtraction problems, we need to learn a very valuable tool for the practicing mathematician. This is called the method of complements. First, we have to answer the question, how far are these numbers from 100? Look at them. Okay, and these are the answers. Now, what do those answers have in common? Well, notice that the leftmost digits always add up to 9, and the rightmost digits always add up to 10. Did I say always? Well, almost always. There's one exception. Okay? The exception is if the number ended in 0, as was the case with 60, then we already knew how far that was from 100. That was 40, and that was very easy. But if the number doesn't end in 0, then the left digits add up to 9, and the right digits add up to 10. And if you think about it, that makes sense. Here, you try these. How far are these numbers away from 100? Okay, got them? Thinking of them? All right, what were our answers? We got 51, 72, 14, 09, 21, and the last one was 20. Got it? All right, let's try a more complicated subtraction problem now. 824 minus 386. Okay, I'm not going to subtract one digit at a time because that 80 is going to really give me trouble. What I'm going to do is I'm going to subtract too much. I'm going to subtract 400. Okay, 824 minus 400 is 424. But I've subtracted too much. How much too much? Well, how far is 386 from 400? Well, it's the same as how far is 86 from 100. And we know the complement of 86 is 14. So we have to add back 14. So we're holding on to 424. We add back 14, and the answer is, yes, 438. Okay, let's try one problem for you to do. Let's try 717 minus 268. So subtract 300, that's right. 717 minus 300 is 417. Add back the complement of 68. What's that? Right, 32. 417 plus 32 from left to right is 449. You got it. Okay, let's go back and see how Chris did his subtraction problem. What were the numbers again? 1,231 minus 589. Let's watch this for a moment.
What is 1,231 minus 589? How much is that?
642.
Yep, in his head. Look at that. Can you believe that?
Okay, 1231 minus 589. The first thing he did was he subtracted 600. He probably subtracted 600 as soon as he heard the 589 being pronounced. Okay, 1231 minus 600 is 631. Add back the complement of 89, which is 11. 631 plus 11 is 642. Phew, you got that one? Give yourselves a pat on the back if you did. Before we begin doing even larger subtraction problems, we have to do three-digit complements. How far are these numbers from 1,000? Here are the answers. Now, except for the last two problems, what do these answers have in common? Well, the first digits always add up to 9, the second pair of digits add up to 9, and the last pair of digits will add up to 10. So the complement of 2, 4, 6 would be, well, what number adds to 9? 7. What number from 4 do you have to add to get 9? 5. And what number do you have to add to 6 to get 10? 4. So the complement is 754, which we did from left to right. If the number ends in 0, like with 480, the complement will end in 0, and now we just take the complement of 48, which we already know how to do. That's 52. Okay, and the complement of 700 is, of course, 300. You think you have the hang of it? If not, do some problems in the workbook, but let's give it a try anyway. How far are these numbers from 1,000? The answers should be 471, 139, 253, 630, and of course, 200. Now, do you remember from the show when little Taylor found the exact change from a $100 bill for $14.39? Let's take a look at that.
I already know mathematics.
Really? Can we test you?
Well, I know how much change you're supposed to get back.
Wait a second. You figure out how much change for my $100? How much change?
$85.61.
Is that right? Right on the button. That's pretty good.
We explained how he did that problem. In fact, let's look at our explanation from there. Now, if you tried to do that problem the old-fashioned way, it would just be a nightmare.
You could never do that in your head.
I don't think so, but let me show you how easy it is to do using Mathemagics.
Okay.
Let's say the purchase price was $14.39.
Right.
Now, to make change from $100, all you need to know how to do is subtract numbers from 9 and subtract numbers from 10.
How's
You'll
that?
subtract every number from 9 except the last one, which you subtract from 10. Let me give you an example. Okay, what's 9 minus 1?
8,
And 9 minus 4?
5,
And 9 minus 3?
6,
And 10 minus 9?
1.
And that's the answer, $85.61.
That's it. That's pretty easy.
All Taylor was doing was taking a complement of the number 1439 to get 8561. Now, Mike asked, well, what if the amount of change had been different? Suppose, say, a $50 bill had been left on the table instead of a $100 bill. No problem. All you'd have to do is subtract $20 from 50, subtracting too much, giving us $30, and then we add back the complement of 439. The complement of 439 is 561, so the change would have been $35.61. If he had left a $20 bill in the envelope, then when we subtract $20, we'd be left with nothing. We add back the complement of 439, and that's our exact change, $5.61. As long as we're on the subject of money, I'd like to conclude this module by talking a little bit about checkbook math. Unfortunately, most of the math that I do in my checkbook is subtraction. Let's start with the problem $123.45 and subtract $67.18. Now, what I'm about to give you is a pencil and paper method. I would not do this entire problem in my head. That would just be a little bit too much of a memory burden. Let's start. I always break the problem into two parts. I do the cents, and then I do the dollars. Suppose I want to start by subtracting 45 cents minus 18 cents. Well, 45 minus 18 is 27, so I write down the cents to get 27 cents. Next, I'll do $123 minus $67, and I'll do this much in my head. I'll subtract $100. Then I'll add back the complement, which is 33. So I have $23 plus $33 is $56, and I'll write that in. So that's my answer, $56.27. But let's suppose now the problem was just a little different. Suppose it was $123.45, and now we were subtracting $67.89 instead. So once again, I'll start with the cents. I'll do 45 cents minus 89 cents. Well, gosh, 89 cents, that's too big. Let's just take the complement of 89 and add that to 45. 45 plus 11 is 56 cents. I write that down. Then now I've borrowed $1 in doing this calculation. So I either have to say 122 minus 67, or sometimes I think of it as 123 minus 68. Take your pick. We'll do it the first way. 122 minus 67, 122 minus 100 is 22. Add back the complement of 67, which is 33, giving us $55.56. Okay, finally, on an upbeat note, let's end it with an addition problem for the checkbook. Let's say I had $123.45. I wanted to add $67.89. First we do the cents, then we do the dollars. 45 cents plus 89 cents would be $1.34, so we write down the 34. Add the dollar to the 123 gives us $124, which when we add it to the $67 gives us $191. So that's the answer, $191.34. Hopefully you'll be doing a lot more adding than subtracting in your checkbook as well. How would you like to learn how to multiply? You can either watch these guys or listen to me. Now we come to my favorite operation, multiplication. I assume you know your multiplication tables through 10 and are fairly comfortable with multiplying one-digit numbers together. If not, you need to consult the booklet and the audio tape. Let's do as our first example 42 times 9. Now, just as with addition and subtraction, we do all of our multiplying from left to right also. So we'll start with 9 times 40. Well, 9 times 4 is 36, so 9 times 40 is 360. Next, we do 9 times 2, which is 18. Add those numbers together, from left to right, of course, and we get 378. Here, you try this one. 64 times 3. What's 3 times 60? 180. 3 times 4 is 12. Add those numbers together, and you get 192. Again, if this is going too fast for you, please make judicious use of that pause and rewind button. That's what I'm here for. Okay, here's another one for you to try. These are very important to master before we can do very big problems. Let's try 37 times 7. Okay, what's 7 times 30? 210, right? 7 times 7 is 49. Add 210 plus 49 and you get 259. If you practice these enough, you'll be able to do these problems very, very quickly in a matter of seconds. Here are a couple that you could probably do very quickly already. These are some easy ones. How about 83 times 3? Well, 3 times 80 is 240. 3 times 3 is 9. Notice there's really no overlapping digits. 240 plus 9 is 249. Okay, here's another easy one. 67 times 5. 5 times 60 is 300. Hey, look at those 2 zeros there. They're going to help us out enormously because there's nothing I'm going to be able to add to that that's going to change that 300 into a 400 or anything. We can even say the 300 right now. Say it, 300. Now we do 5 times 7, which is 35. Say it, 35. And that's the answer, 335. I'll do a couple more problems that are a little more difficult because they involve some carrying. Let's try 18 times 7. Okay, from left to right, of course. 7 times 10 is 70. 7 times 8 is 56. 70 plus 56 is 126. All right, how about trying this one? 76 times 7. This is tougher. 7 times 70, well, 7 times 7 is 49, so 7 times 70 is 490. 7 times 6 is 42. Add 490 plus 42. Well, 49 plus 4 is 53, so 490 plus 42 is 532. Let's do one more example. 26 times 9. All right, 9 times 20 is 180. 9 times 6 is 54. Add 180 plus 54 gives us 234. I'm going to do another multiplication problem, 59 times 7, but I'm going to do this one 2 different ways so you can see the variety. 7 times 50 is 350. 7 times 9 is 63. 350 plus 63 from left to right is 413. But let me show you another way of doing that problem, which you might even find easier this first time around. Let's treat 59 as 60 minus 1. And now do 7 times 60, and then subtract 7 times 1. 7 times 60 is 420, minus 7 gives us 413. Was that easier than the first way? It probably was. Let's do another example of that sort. Let's do 79 times 8. Okay? This time I'll do 8 times 80, which is 640, minus 8 times 1. 640 minus 8 is 632. Okay? Let's do one more 2-digit multiplication problem. Let's try 68 times 7. We'll do this 2 ways. First, what I'll call the addition method, then the subtraction method. 7 times 60 is 420. 7 times 8 is 56. 420 plus 56 is 476. The subtraction method, we would start by doing 7 times 70 and treat 68 as 70 minus 2. 7 times 70 is 490, minus 7 times 2, which is 14. 490 minus 14, that's 476. Frankly, I prefer doing the addition method for that problem. In fact, I always use the addition method because by the time it takes me to decide whether I should be adding or subtracting, I could have done the problem already. So I recommend doing the addition method primarily for 2-digit numbers times 1-digit numbers. Okay, now, go in your workbook and practice 2-digit numbers times 1-digit numbers because you won't be able to do the next group of problems until you're very good at doing those. Have you practiced doing your 2-digit numbers times 1-digit numbers? I hope so, because otherwise these next problems will be very difficult indeed. Let's try. I like to do everything by example. Let's start off with 628 times 7. Once again, we do all of our calculating from left to right. I'll start with 7 times 600 to give us 4,200. Now, let me pause for a moment here. Because we're working from left to right, we know already that the answer has to be a little higher than 4,200. And that's very important. In fact, if we were to stop the calculation right now, we could say, the answer is a little bit over 4,200. But if we were working from right to left like we do on paper, all we would know is that the answer ended in 6. And that's not very important. Okay, end of lecture. Let's go back to the calculation. 7 times 600 is 4,200. 7 times 20 is 140. Now at this point, ladies and gentlemen, I stop. Before I do 7 times 8 to get 56, I stop to add 4,200 plus 140. Left to right, of course, giving us 4,340. Got it? Now we do the 7 times 8 to get 56, add that to 4,340, and the answer is 4,396. Phew. It takes a little while before you can hold all these numbers in your mind, but once you do, once you practice it enough, and of course you've got to practice. Once you've practiced it enough, you'll be able to do these problems in a matter of seconds. These are so important, I'm going to do a few more examples. Some 3-digit numbers times 1-digit numbers are easier, some are harder. Let's start off with some of the harder ones. Let's get those out of the way, and then we'll do some easier 3-digit times 1-digit problems. Let's do 373 times 4. Okay, left to right, 4 times 300 is 1,200. 4 times 70 is 280. Now add 1,200 plus 280, and you get, listen to yourself, 1,200, 280 gives us 1,480. Now I do 4 times 3, which is 12. Add that to 1,480, and we get 1,492, which was the year Columbus discovered America, right? Okay, here's another historical problem. Try 296 times 6. Okay? 6 times 200 is 1,200. 6 times 90 is 540. 1,200 plus 540 is 1,740. You see where we're heading? Now 6 times 6 is 36. 1,740 plus 36 is 1,776. That's the spirit. Hey, I got an idea. Let's do that same problem a slightly different way. Let's do 296 times 6, and let's treat 296 as 300 minus 4. So I'll do 6 times 300, and then I'll subtract 6 times 4. 6 times 300 is 1,800. Minus 6 times 4, which is 24. 1,800 minus 24, what's the complement of 24? It's 76. So the answer is 1,776. Now let's try some easy ones. 805 times 3. I promised this was going to be easy. 3 times 800 is 2,400. 3 times 5 is 15. 2,400 plus 15 is, you can hear it, 2,415. Here's another one. 573 times 6. Doesn't look as easy, but it is. Start with 6 times 500. That's 3,000. You can now say the 3,000. You don't have to worry about 73 times 6 because it's just going to be a 3-digit number of some sort. Say the 3,000. Now do 73 times 6. That's 420 plus 18 is 438. And that's the rest of your answer. 3,438. Here, you try this one. 649 times 5. 5 times 600 is, say it, verbally, say it, 3,000. Good. 5 times 40 is 200. Heck, you can say that too. I love fives. They're so convenient. 5 times 9 is 45. And that's the answer, 3,245. I want to show you 2 more 3-digit times 1-digit numbers that sort of break the pattern that we've established. I'm going to do 811 times 7. Okay, I'll start with 7 times 800 to get 5,600, and now I'll do 11 times 7 in one fell swoop, because I know that 7 times 11 is 77, so why not just do it? 5,600 plus 77 is 5,677. Wasn't that easy? Let's try 425 times 8 as my last example. Again, I'll start with 8 times 400 is 3,200. And now I take advantage of the fact that I know that 25 times 8 is 200, right? Because if you had 8 quarters, that would make exactly $2, right? So 8 times 25 is 200. Add that to the 3,200, and now you have an even 3,400. Actually, we can apply this problem to do problems involving percentages. For instance, suppose you bought a VCR for $425, and that the sales tax on that VCR was exactly 8%. Well, we've just done the calculation that you would need to do to determine what the sales tax would be, because taking 8% of something is just multiplying it by 8 and then dividing by 100. And since 425 times 8 is 3,400, when you divide it by 100, you're left with an even $34. Here, let's do one more problem for you to try. Let's say you bought a camera for $240 and that the sales tax was 7%. Okay, let's do 240 times 7. 7 times 200 is 1,400. 7 times 40 is 280. Add those to get 1,680. Right? And now what do? You take 1,680 divided by 100 to be left with 16.80. In other words, $16.80. Which, when you add it to the price of the camera of $240, would give you a total bill of, not too hard to do in your head, left to right, $256.80. Well, that wasn't too bad, was it? Maybe the next time you're asked to divide the check, you won't have to resort to this. Let's talk about division now. If you think about it, division is the only operation that we're taught to do in school from left to right already. Think about it. I suppose if they could figure out a way of teaching you division from right to left, they might, but until that day comes, we're all going to be doing it from left to right. Let's try a simple division problem like 65 divided by 7. You need to know your multiplication tables through 10 pretty thoroughly for you to do this. You ask yourself, how many 7s can I squeeze into 65? 7 times 9 is 63. 7 times 10 is 70. Well, that's too much. So 65 divided by 7 will be 9 with a remainder. When I subtract 63 from 65, I get 2. So my answer is 9 with a remainder of 2, or 9 2/7. Okay, your turn to try this one. 47 divided by 8. All right, well, let's see. 8 times 5 is 40. 8 times 6 is 48. Well, that's a little too high, so the first number is 5. What will our remainder be? 47 minus 40 is 7, And so the answer would be 5 with a remainder of 7, or 5 7/8. All right, let's go up a level. Let's try 3-digit numbers divided by 1-digit numbers. The answer will always be either a 2-digit number or a 3-digit number. For example, let's try 326 divided by 9. Now, let's see, that answer would be 36 2/9. Let me show you how I do that. First, I try and see how many 9s I can squeeze into 326. I see that 9 times 30 is 270. 9 times 40 is 360, which would be way too big. So the first part of my answer is 30. And I'll say the 30. I'll get it out of my memory and give myself an easier division problem. I've now subtract 270 from 326, giving me 56. So my new division problem becomes 56 divided by 9. Oh, that's easy, because 9 times 6 is 54. So the answer is 36. Now all I have to do to figure out the remainder is subtract 54 from 56, which is 2. So the answer is 36 with a remainder of 2, or 36 2/9. All right, here, you try this one, 523 divided by 6. Okay, first of all, how many 6s can you squeeze into 523? 6 times 70 would be 420. Can we go higher? 6 times 80 is 480. Can we go higher? 6 times 90 is 540. Too late. You went above 523. So 6 times 80 is 480. Say the 80. Let me hear it. 80. Right. Okay, now subtract 480 from 523. What do you get? Well, if you're good at subtraction, you should get 43. Okay, 43 divided by 6 is, oh, that's easy, that's 7 with a remainder of 1. So the answer would simply be 87 with a remainder of 1, or 87 1/6. Okay, finally, let's do a 3-digit number divided by a 1-digit number that gives us a 3-digit answer. Let's say 655 divided by 3. Okay. How many 3s can I squeeze into 655? Well, 3 times 100 is too small. 3 times 200 is 600. That looks just about right. So we'll say 200. Now subtract 600 from 655, leaving us with 55. So we've said the 200, and now our problem reduces to 55 divided by 3. Well, let's see. 3 times 10 is 30. 3 times 20 is 60. That's too high. So I can next say the 10. Okay. And subtracting 30 from 55 gives me 25. How many 3s go into 25? 8 with a remainder of 1. So the answer is 218 1/3. Let's apply this to the following restaurant situation. Imagine the bill came to $57.24, and let's say there were 4 of you to divide the bill. Evenly, of course. Well, I break this problem down into 2 parts. First, I'll divide 4 into $57, and then, depending on the remainder, I'll divide 4 into the rest. Let me illustrate. How many times does 4 go into 57? Well, 4 times 10 is 40, which when I subtract from 57 gives me 17. How many times does 4 go into 17? 4 times. So 4 times 14 is $56. So you can say $14 right away. 4 times 14 is $56. Subtract that from $57.24, leaving us with $1.24. So the problem has been reduced to dividing 4 into $1.24. 4 times 30 cents is $1.20. Subtract that from $1.24, you're left with 4 cents. 4 goes into 4 once, so you get exact answer of $14.31. Okay, let's try another problem. Let's suppose instead of 4 people at the dinner table, we had 6. Okay? How many times does 6 go into $57? Well, 6 times $9 is $54, so you can say $9. Subtract that from 57, you're left with $3, and let's not forget the 24 cents. How many times does 6 go into $3.24? Remember, you've said the $9 already. 6 times 50 is $3, 300. So the next amount will be 50, and all that you're left with when you subtract $3 from 324 is 24 cents. So, and 6 goes into 24 evenly. That was convenient, leaving us with 6 times 4 is 24. So the answer is exactly $9.54. Finally, let's pretend instead of having 4 people at the dinner table, we had 5. I saved 5 for last because that's actually the most fun. That's the easiest one. To divide a number by 5, it's usually a lot easier to multiply the original number by 2, that is, double it, and then divide that new number by 10. See what I'm saying? If I have $57.24 and I double it, I get $114.48. Now, dividing by 10 is a piece of cake. Just slide the decimal point over by 1, and you're left with 11.448, which is roughly $11.45 per person. Now, go to the workbook, practice more division exercises, and soon you'll find yourself conquering that great divide yourself. Whether you're in the laboratory, in the kitchen, or at the mall, you have to know about fractions. I hear from so many people that they understood math just fine until they encountered that dreaded F word, fractions. Well, I think that F should stand for fun, because once you understand how to do simple arithmetic with whole numbers, it's just as easy to do them with fractions. Let's start by multiplying fractions together. That's actually the easiest operation with fractions. Let's say you wanted to do 3/4 times 5/7. Okay? All you do is you multiply the top and you multiply the bottom. What could be simpler? 15 divided by 28, 15/28 is the answer. I won't even do any more examples of that because that's so easy. We've got more examples in the workbook anyway. Dividing fractions is practically as easy. If you think about it, division is the reverse of multiplication, and dividing fractions is kind of like multiplying in reverse. Let me give you an example. Suppose the problem was 3/4 divided by 5/7. We take the second fraction, 5/7, and we reverse it. By that I mean we turn it upside down so it becomes 7/5, 7/5. And now you multiply those two fractions. So 3/4 times 7/5 is 21/20, or 21/20. Okay, here you try this one. Try 2/3 divided by 3/11. Okay, what do? You take 3/11 and you reverse it, so it becomes 11/3. Multiply 2/3 times 11/3, and you get 22/9, 22/9. Exactly. Now, the answer we have there, 22/9, can be simplified. Whenever the number on top, we call that number on top, by the way, the numerator, that's a fancy term we use, is bigger than the number on the bottom, called the denominator, then the answer can be simplified. We have 22/9. We can think of that as a division problem. 22/9, that's 2 with a remainder of 4, or we can just say our answer as 2 4/9. Was I clear on that one? Here, let's do another example. 38/5. The numerator is 38, the denominator is 5. Since the numerator is bigger than the denominator, we think of that as a division problem. How many times does 5 go into 38? Right, 7 times with a remainder of 3. So the answer would be 7 3/5 is a simpler way of expressing 38/5. The next thing I want to talk about is we can simplify another way. If I took a number and multiplied it by 1, that wouldn't change the number, right? You know that. So if I took the number 1/2 and I multiplied it by 1, it would still be a half, right? Of course, right. Okay, now suppose I replace 1 with something that's just the same thing as 1, let's write 2 over 2. 2 over 2 is the same as 1, right? If I take 1/2 and I multiply that by 2 over 2, that gives me what? 2 over 4. And since 2 over 2 was just the same as 1, we must have that 2 over 4 is the same as 1 over 2. That is, 2/4 is the same as 1/2. Similarly, if I took 1/2 and I multiplied it by 1, but now I disguised 1 as 3 over 3, I should get the same thing. And 1/2 times 3 over 3 is 3 over 6. So that means that 3/6 is also equal to 1/2. Do you see that? That those two fractions are the same thing. They represent the same quantity. Okay? By the same logic, if we can divide the top and the bottom by the same number, we'll still have the same fraction. Because really what we're doing is we're dividing by 1, and dividing by 1 gives you the same number. For instance, let's say you were looking at the fraction 27 over 36. Now what's the biggest number you can think of that divides into the top and divides into the bottom? 9, right? 9 times 3 is 27. 9 times 4 is 36. If I divide both the top and the bottom by 9, all I'm left with is 3 over 4. So 27 over 36 simplifies to the fraction 3/4. Now for a practical application. Let's suppose you had a recipe that would show you how to make, 3 dozen chocolate chip cookies. And the recipe called for 3/4 of a cup of chocolate chip cookie dough. But you don't want 3 dozen cookies, you only want 2 dozen cookies. So the question is, how much cookie dough are you going to need? Well, since you don't want 3 dozen, you only want 2 dozen, that means you're going to have to make 2/3 the amount of cookie dough. That's 2/3 the amount of cookie dough is how much you're going to have to use. So we take 3/4 of a cup times 2/3, multiply those together, and we get 6/12, which of course can be simplified to 1/2 a cup of cookie dough is how much you'd need to make 2 dozen cookies. Before we go any further, now would be a good time to go back to the workbook and practice, practice, practice. That's what you need to be able to get very good at doing fractions. Okay, now we come to the next step, which is adding fractions, which is actually a little bit trickier than multiplying and dividing. The easiest problems to do are when the denominators, that is the numbers on the bottom, are the same. For example, let's suppose you wanted to add 3/10 plus 4/10. Okay, all you have to do is add the numerators and keep the denominators the same, and you get 7/10. You see, let's do one more example for you. Suppose you wanted to add 9/16 plus 3/16. Add them together, what do you get? You should get 12/16, which can be simplified to 3/4, because the top and the bottom are divisible by 4. What if the bottom numbers, the denominators, are not the same? Let's suppose you wanted to add 3/16 plus 1/4. Okay, now the denominators are different, but we can make them the same. And the way we do that is we say, 4 divides into 16, so I can write 1/4 as 4/16. If I multiply the top and the bottom by 4, 1/4 becomes 4/16. And now the problem becomes adding 3/16 plus the same number, 4/16, which of course is 7/16. Was that a little confusing? Here, let's do one more example and you'll catch on. Try adding 1/5 plus 3/10. Okay, we're lucky here because I can multiply 2 times 5 and get 10. So let's multiply the top and the bottom by 2. So 1/5 is the same as 2/10. I'm now going to add that to 3/10, and we get what? 5/10, exactly. And 5/10 simplifies to 1/2. Okay, now suppose the denominators are different and you can't just multiply one by something and get the other. Like let's say 3/4 plus 5/7. Okay? Well, I'm going to make the denominators the same by multiplying the first fraction by 7/7 and the second fraction by 4/4. So this makes the first fraction equal to 21/28, the second fraction equal to 20/28. Add 21/28 plus 20/28. Now the denominators are the same, and we get 41/28. Which, by the way, if you wanted to simplify that fraction, well, since 41 is bigger than 28, we can simplify that to 1 and 13/28. Okay? You want to see one more example of this difficult problem, kind of problem? Let's add 1/2 plus 5/9. Okay? So multiply top and bottom of the first fraction by 9 gives me 9/18. I chose 9 because that was the other denominator. I'll multiply 5/9 by 2/2 to give me 10/18. We add 9/18 plus 10/18, and that gives us 19/18, which, if you want to simplify, is 1 and 1/18. Finally, subtraction's a lot like addition. If the problem was, say, 4/10 minus 3/10, then just go ahead and subtract the numerators and you get 1/10. Okay, so here, if you wanted to subtract 9/16 minus 3/16, what do you get? 6/16, of course, which simplifies, by the way, to 3/8. I like simplifying things. I like to keep life as simple as possible. Okay, let's try, now the denominators are different. Let's try 1/4 minus 3/16. What do? We want to get both denominators to be the same. Let's multiply the first fraction by 4/4. So we have 4/16 minus 3/16, and now it's easy. The answer is simply 1/16. Okay, here, you try it. Try 8/9 minus 2/3. Okay? What are you going to do? Let's convert 2/3 into a fraction that'll have 9 on the bottom. Okay, so I'll multiply top and bottom by 3. So 2/3 becomes 6/9. Right. So 8/9 minus 6/9 is simply 2/9. That wasn't so hard. Okay, one last, this will be the toughest of them all. Let's try subtracting 7/10 minus 2/9. Okay, 7/10 minus 2/9. Well, 9 and 10, well, neither of those divide into each other. So I'm going to multiply the fraction 7/10 by 9/9 and the fraction 2/9 by 10/10. So my first fraction becomes 63/90. My second fraction becomes what? 20/90. 63/90 minus 20/90 is 43/90, which is the answer to the problem, 7/10 minus 2/9. Okay, before we go any further, I insist you take some time and practice using problems from the work booklet. And then when we get back, we'll do some more interesting stuff with fractions that'll amaze your friends. The last thing I want to talk about is how to convert a fraction into a decimal. If the denominator is 11 or smaller, then that process is very, very easy, and it's explained in the workbook. Okay? The only denominator I want to talk about, give special attention to now, is when the denominator is 7, because it's so amazing, it's so magical that I got to show it to you. I don't want to just let the book show it to you. Okay? Let's look at the fraction 1/7. Okay? If you were to expand it into decimal notation, you would get 0.142857, 142,857, 142,857, and so on, repeated forever. Okay? All you have to remember is those numbers, 142,857. Next, let's look at the fraction 2/7. 2/7 is also a repeating fraction, but it goes 0.2 285714, 285714 repeated. But do you see that that's the same numbers as we had before, just shifted over by a little bit? Right? We have the 285714. Similarly, 3/7 is 0.428571 repeated. It's the same 6 numbers, except they start with the number 4 this time. 0.428571, 428571, and so on. Okay? 4/7 is 0.571428 repeated. 571428, and so on. Okay? 5/7 is 0.714285 repeated, and 6/7 is 0.857142 repeated. So once you memorize that original cycle, 142857, then you've got all of them memorized. Okay? Now, if ever you were given a division problem where you were asked to divide something by 7, let's say the problem was 45 divided by 7. You could say the answer is 45/7, but that's not really saying very much. Or you could say the answer is 6 and 3/7. That sounds nice. But if you really want to sound like a genius, you'll say 6.428571, 428571, 428571. There are times when all you need is a good mental estimate, such as when you're reading the stock page or verifying the numbers that your calculator spits out. One of the great advantages of working from left to right is that you work with the most significant digits from the start. And oftentimes, that's all you really need to get a good estimate of your final answer. For example, suppose we wanted to add 3,417 plus 6,195. Now, gosh, that's a lot of numbers to hold in memory, and you don't even maybe want the exact answer. Let's just approximate the two numbers with, let's say the first number is approximately 3,400, and the second number is approximately 6,200. Add those numbers together and we get 9,600, which is very close to the exact answer of 9,612. Okay? Let's try a larger problem, but it's just as easy if you want an estimate. Let's say you wanted 23,456 plus 56,789. Okay? Let's just round to the two most significant digits. 23,456, that's approximately 23,000. And the second number is closer to 57,000 than the 56,000, so we'll call it 57,000. Now we add 23,000 plus 57,000 to get 80,000, which is almost the exact answer. You probably couldn't even hold on to that entire problem in your head unless you used some of the advanced memory devices that we teach in the advanced video. But if you just want an approximation, this will do just fine. Subtraction, just as easy. Let's say we wanted to do 6,195, and this time instead of adding it, we'll subtract 3,417. The first number is about 6,200. The second number is about 3,400. Subtract those numbers and you'll get about 2,800. And it's as easy as that. Now, I don't actually compute my grocery bill to the exact penny when I go shopping. You remember Todd did that on our television show. And let's see what he did exactly, and then I'll show you how you could have done the same thing approximately. Okay, let's have a look at it.
Can we give you a little test?
Take your best shot.
Oh, he's pretty confident. Also joining us on today's show is Tony from Tony's Deli. Welcome back, Tony.
Hey, yo, Mike, how you doing today?
Now, before today's show, our crew did a little bit of shopping at Tony's Deli. We have some items there ready to get checked out. And Tony, I want you to check them out using your cash register. Go ahead.
No problem, Mike. Listen, 325 is the first item. Amazing brand. Good stuff. Had it this morning. I got it for 80 cents. I got on special for you. Myco meal.
Who
One
thought
of
of
my
that
favorites.
one?
$5.99. Microwave popcorn. Good for some late night
That's
TV
silly.
viewing. And at $4.35, if you're a couch potato like my cousin Vinny, eat these all night, chucked full of nuts. You want me to total this up, Mike?
Now, don't push the total button. Wait, Tony, because Todd's going to tell us how much we spent so far at Tony's Deli. How much we spent?
You spent $14.39.
Is that right? Right on the button. That's pretty good.
All right, now you see what he's done here, $3.25 plus 80 cents. Adding that left to right, that's not a problem, right? It's $4.05. Okay, what was the next item?
$5.99. Microwave popcorn.
Okay, $5.99. Okay, well, let's add $6. That gives us $10.05, but we got to subtract a penny, giving us $10.04. Oh, that's an easy number. Let's now add $4.35 to $10.04 to give us
$14.39.
which was his answer. Nice going, Todd. But if you just wanted to get an approximate answer, here's what I do. As the numbers are being called out, I will always round the numbers either up or down to the nearest 50 cents. If I'm exactly between a dollar, even dollar amount, and a 50-cent amount, like if I had 25 cents or 75 cents, I'll just go to the even dollar amount because that's easier to work with. All right, so let's run that again, and this time I'll see how we could have done that just using approximation.
$3.25 is the first item. Amazing brand. Good stuff. Had it this morning. I got, for 80 cents, I got on special for you. Myco meal.
Who
One
thought
of
of
my
that
favorites.
one?
$5.99. Microwave popcorn. Good for some late night
That's
TV
silly.
viewing. And at $4.35, if you're a couch potato like my cousin Vinny, eat these all night, chucked full of nuts.
Okay, the first item was $3.25. Take your pick. You want $3, you want $3.50. I'll call it $3 because that's easier. Okay, the next item was what? 80 cents. Well, that's closer to a dollar than to 50 cents, so I'll add a buck. So now the answer is $4. At least that's my approximate answer. The next item was $5.99. Oh, that's easy. Just add $6 even, so we have $10. And finally, $4.35. Let's round that up to $4.50 because it's closer to $4.50 than it is to $4. And so my approximate answer would be $14.50, which is only off by 11 cents. If you do this even for very large lists, your answer will usually be within about $1 or so from the actual answer, which for me is quite good enough. One of my favorite calculations is squaring. That is, taking a number and multiplying it by itself. For instance, 5 squared is 25. Now let's watch part of my show at the Magic Castle, and afterwards I'll show you how I do it. What I'm going to try and do now is to square 4 two-digit numbers in my head faster than they can do on the calculators, even using the shortcut method. What I'll ask is for the 4 of you here to each call out a single two-digit number, and if you would square the first, the second, the third, and the fourth, I will try and race you to the answer. So quickly, a two-digit number, please.
84.
84.
23.
23.
57.
57. 79. Would you call out your answers, please? 7,056. 529. 3,249.
6,249.
Thank you very much. One of my favorite calculations to do is squaring numbers. That is, taking a number and multiplying it by itself. For instance, 5 squared is 25. Let's try squaring some two-digit numbers. These are very easy to learn, and once you've learned them, you'll look like a genius without really trying. We'll start off small and work our way up. Let's start with, say, 13 squared. 13 is not an easy number to multiply by, but what number close to 13 is? 10, right. Now, you have to go down 3 to get to 10. Now, whatever comes up must come down, or whatever comes down must come up, is what I think. If I go down 3 to 10, I must go up 3 to 16. So the first part of my calculation is I multiply 10 times 16. That's easy. That's 160. We're almost done. All we have to do is to add the square of the number we went up and down. We went up and down 3. 3 squared is 9. And so the answer is 160 plus 9, which is 169. And that's all there is to it. Now, the reason why this works is explained in the booklet, but let's go on. Let's try 28 squared. Okay, now 28, this time I'll go up 2 to 30. If I go up 2 to 30, I must go down 2 to 26. Now what's 30 times 26? Now don't panic, that's just 3 times 26 with a friendly 0 attached. 3 times 26 is 78, so 30 times 26 is 780. Almost done. All we have to do is add the square of what number? 2. Good. 2 squared is 4. And that's the answer, 784. Here, you try this one. This one's even easier. 75 squared. This time we'll go down 5 to 70. And up 5 to 80. Now what's 70 times 80? Piece of cake, right? It's 5,600. Almost done. All we have to add to that is the square of the number we went up and down. 5 squared is 25. 5,600 plus 25 is 5,625. You can actually hear the answer. All right, let's do one that's a little bit tougher, but not too much. Let's try 59 squared. Okay, we go up 1 to 60. Down 1 to 58. 60 times 58. Well, 6 times 58 is 348. So 60 times 58 is 3,480. Add to that the square of 1, which is 1. 3,480 plus 1 is 3,481. By the way, if that 60 times 58 problem gave you some difficulty, you should review the 2-digit numbers times 1-digit numbers covered in the multiplication module. Okay, quiz time. Try and do this one in your head. All right, and use that pause button when you think you have the answer. You can push the pause button again. 96 squared. Now hit that pause button. Okay, I'm about to say the answer. The answer is 9,216. Is that the answer you got? If not, go ahead and rewind and try and do it again and see if you can get that answer. Okay, here's how we got 9,216. We went up 4 to 100, down 4 to 92. 92 times 100 is 9,200. Add to that the square of 4. 4 squared was 16, and that's the answer, 9,216. If you got that right within the first 2 tries, congratulate yourself as being a budding mathemagician. Let's try a problem now of the sort that you might see on the SAT exam. This isn't really a calculation problem, but it's one that requires understanding where squares come into play. The problem might be as follows. Which of the 2 squares on the screen has the larger area? The square whose sides are all of length 6, or the square that lies on that right triangle whose sides are of length 3 and 4? The square on the left will have an area of 6 squared, which is 36. The square on the right, well, here's where good old Pythagoras comes into play. Pythagoras says that if I have a right triangle with sides A, B, and hypotenuse C, then the A squared plus B squared will add together to give me C squared. And if I had a square lying on that hypotenuse, its area would be c squared. Now what is c squared here? It's 3 squared plus 4 squared. That's 9 plus 16, which is 25. So the area of the second square is 25, which is less than the area of the first square. By the way, it also tells us that the hypotenuse had to have a length of 5. Now let's go on and do one last calculation, let's say a 3-digit square. This is a sort of problem that we do of in much more detail on the advanced video, but I've included this one here for sentimental reasons because it's the first 3-digit square that I ever calculated. Suppose we wanted to square the number 108. This time we'll go down 8 to 100. We'll go up 8 to 116. Now 116 times 100, that's just 11,600. Almost done. All we have to add to that is the square of 8. The square of 8 is 64, and there's your answer, 11,664. Now do some problems in the workbook, and you'll be impressing your friends in no time. Wouldn't you say that to be a mathematical wizard, you need to learn algebra?
Absolutely.
Perhaps the most important subject to learn when taking the SAT is algebra. And in order to master this most serious of all subjects, I've decided to introduce it with something that's very fun. Magic tricks. Let's start off with a trick that you can help me with at home. I want you to think of a number between 1 and 10. You can think of a larger number, but for this first experiment, just keep it between 1 and 10. It'll be easier that way. Now, take that number and double it. All right? Now add 10 to the number that you're thinking of. Now, take what you're thinking of and divide that number by 2. Okay? Got it? Now subtract the number that you originally started with and concentrate on that answer. I think you're thinking of the number 5. Is that right? Good. And now let me explain how to do that using algebra. I did not know what number you thought of. Admittedly, a lot of people think of 3 or 7 to begin with, but it could have been any number. Let's call that original number x. That's the most famous number in algebra, x. Now, that stands for something we don't know. Now, what was the first thing I asked you to do? To take that number and double it, right? So if we started with x, then now we have 2 times x. Now, we won't write a times symbol. That would be confusing. It would look like 2xx, and we wouldn't want that. So we'll just call that 2x. Next, what did we do? We added 10 to that number. Okay? So now we have the number in our minds 2x plus 10. Next, you took that number, 2x plus 10, and divided it by 2. Well, let's divide each term by 2. 2x over 2 is x. 10 over 2 is 5. And so now you're holding on to the number x plus 5. Finally, you were asked to take that number and subtract the number you originally started with. What was the number you originally started with? It was x. So x plus 5 minus x leaves you with 5. You have to end with 5. And that's the best example of algebra that I can think of for getting us started. For my next trick, go and bring a calculator to the television set if you don't have one with you. Go ahead, press the pause button, I'll wait. Okay, you have a calculator now. I'd like you to enter a 3-digit number on the calculator, with the only requirement being that the first digit has to be larger than the last digit. Okay? So for instance, I'll choose the number 781 because 7's bigger than 1. But don't let me influence your decision. Go ahead, pick a different 3-digit number. Okay? Now, reverse your 3-digit number and subtract that from your original number. So for instance, if I reverse 781, I get 187. When I subtract that from 781, I get 594. Okay? Now you should do the same with your numbers. All right. Next, if your answer is a 3-digit number, then leave it alone for the moment. Okay? If it's a 2-digit number, like let's say your answer was 57, then attach a 0 to the front of your number. So now you'd have 057. Okay? All right, so now, if you had a 2-digit number, you now have a 3-digit number because it begins with a 0. If you had a 3-digit number as your answer, it's still a 3-digit number. Either way, I'd like you to now take that answer and reverse the digits. Okay, so if I take my 594 and reverse the digits, I get 495. You should do the same. Now add those two numbers together. So if I add 594 plus 495, I get 1,089. What do you get? If you followed my directions properly, you should also get 1,089. And if you want to understand why that'll always work, to see the algebraic explanation, consult the workbook. For my last trick, I'm going to need a volunteer from the audience. But since we don't have an audience here, the closest person near me is the camera operator, Suzanne. Suzanne, would you be willing to help me out on this one? Great. Now, I have a chart here, and I want you to help me out by thinking of a number. Again, let's keep it fairly small. Think of a number between 1 and 10, and enter that number in row 1. But don't let me see it, okay? Now I want you to think of another number between 1 and 10, make it a different number, and enter that in row 2. Okay? Next I want you to add row 1 plus row 2 and write the answer in row 3. Okay? Next add row 2 to row 3 and write the answer in row 4. Then add row 3 to row 4 and write the answer in row 5. And keep on doing that. Row 4 plus 5 gives you row 6, row 5 plus 6 gives you row 7, and so on until you have numbers in all 10 rows. Okay? Next one, thank you. Next what I'm going to do is I'm going to try and add up those 10 numbers faster than you can. Now I haven't seen your numbers yet. I'm going to peek at them right now. I think the numbers add up to 561. Is that what you get? Haha, good. I'll explain how that works using algebra. Okay, I did not know what number you started with, so let's call that number x again. X stands for the unknown number. You wrote another number in row 2, and I didn't know what that one was, but it was a different number, so let's call it a different letter. Let's call that y. Next we add x plus y. When we added row 1 to row 2, we put that in row 3. So row 3 will have x plus y. Next we added row 2 to row 3. And here's where it gets a little tricky. If I add y to x plus y, I get as an answer x plus 2y. Okay? Next, if we take x plus y and add that to x plus 2y, we get 2x plus 3y. If you understood how I did that, then the rest should be smooth sailing. Okay, we take x plus 2y, add that to 2x plus 3y. That gives us 3x plus 5y. Okay, if we add 2x plus 3y to 3x plus 5y, we get 5x plus 8y. And so on. So you can fill in the rest of that chart, right? Okay, so the last number there was 21x plus 34y. Good. Now I want you to add up all of those letters, okay? If we add up all the x's, we've got an x, then another x, a 2x, 3x, 5x, 18x, 13x, 21x. Add all those together, and then we get 55x. And if we add up all the y's, we get 88y. So all those numbers will add up to 55x plus 88y. Now, how did I figure out your answer so quickly? It's based on what's written in box number 7. What's in box number 7? It says 5x plus 8y. If you take 5x plus 8y and multiply it by 11, then by the distributive law, we're going to have 55x plus 88y, which is the grand total. So what I did was I looked at what was written in box number 7, and I multiplied it by 11. Let's see your original numbers again. Okay, now in box number 7, you have 51, which I multiplied by 11 and quickly got the answer 561. And that was your total. Okay? Now I've got one more trick for you. I want you to now take the number that you have written in box number 10. Bring out a calculator for this. Divide it by the number that's written in box number 9. Okay? So in your case, that's 215 divided by 133. Before I began this last trick, I wrote down a prediction on the back of this card. I predicted what would happen if you were to take the number in row 10 and divide it by the number in row 9. Go ahead with the numbers that you have there, which are 215 divided by 133. Okay? Give me the first 3 digits of your answer. Okay? I get, do you get 191? Oh, no. What do you get? 1.61. Oh, I see. That's what I had. I just had the card written upside down. Well, if you want to see why that works, consult the booklet as well. I hope you enjoyed your first exposure to Mathemagics. Thanks for joining.